Mars, or as we call it, the Red Planet. For as long as humanity has gazed at the stars, it has been the second world to capture our curiosity. Shining like a red star, this cold and desolate world is far more complex than it first appears. For hidden upon its surface are traces that whisper an entirely different story. What if we told you that this was once a world where rivers flowed, lakes glistened, and perhaps even seas churned with waves? This planet, which today seems utterly dry, silent, and lifeless, once had a past far more dynamic than we ever imagined. As scientists learn to read the stones, valleys, and mineral signatures of Mars, a stunning picture of a vibrant past is revealed. In fact, some of the most striking evidence suggests that this planet might have once been a suitable home for life itself. But that raises a profound question. How could a world that now appears so barren, frozen, and lifeless have once been as vibrant and habitable as our own blue Earth? And this is where the most critical question of all emerges. If Mars once possessed the conditions to host life, why has it become a desolate desert today? And more importantly, if Mars lost its hold on life, could the same fate one day befall on our own world? When we picture Mars, the familiar image comes to mind: vast red soils, colossal craters, and an empty sky. And yet, if we look a little closer, that desolate picture begins to transform. Because the Martian crust is filled with irrefutable evidence that water once carved its way across this world. The valleys, the dried-up lake beds, the remnants of ancient deltas. They all cry out in unison, telling us that millions of years ago, Mars was much warmer and far more humid than it is today. Take the river valleys, for instance. They are uncannily similar to the great river systems on Earth. The way they branch, merge, and diverge carries the unmistakable signature of water that must have flowed persistently over long periods. There can be only one conclusion. Just like on Earth, rain once fell on Mars, and rivers of water streamed across its surface. But the evidence doesn't stop there. Deltas found in certain regions offer even more powerful clues, as a delta can only form in the presence of a large, stable body of water. Their very existence proves that Mars was a world not only of rivers, but of great lakes, where water pooled for ages inside vast craters. Another remarkable feature is the massive outflow channels. These colossal structures, hundreds of kilometers long and tens of kilometers wide, seem almost alien in their scale. Geologists who study them agree on one thing: they must have been carved by catastrophic floods of unimaginable power. The theory is that vast reservoirs of ice, frozen deep underground, suddenly fractured. The ice melted rapidly, bursting to the surface under the immense pressure and transforming into magnificent floats that reshaped the face of the planet in a matter of weeks. The minerals themselves confirm this watery story. Clay minerals found across the Martian surface can only form when rocks are exposed to water over very long timescales. Their presence is a chemical fingerprint of a past where water and rock interacted for millions of years. At the same time, deposits of sulfate minerals tell of a later period when that water became more acidic. It's clear that Mars' climate wasn't static. It changed dramatically over time, experiencing its own cycles of wet and dry, much like Earth's own history of ice ages and warm spells. So, where did all this water go? This is where the story gets truly fascinating. Mars still has vast quantities of water, just not in liquid form on its surface. Instead, it's locked away as ice at the poles and deep underground. Calculations suggest that if all this known ice were melted, it would cover the entire planet in global ocean tens of meters deep. And that doesn't even account for the possibility of even larger, undiscovered reservoirs hidden deeper still. Today, liquid water simply can't survive on the Martian surface. The atmosphere is too thin and the pressure too low for it to last. It either freezes instantly or boils away into space. But the geological record is unambitious. Mars was once a world on the verge of being blue. It may not have had Earth-like oceans, but it was a dynamic planet, sculpted by the power of its lakes, rivers, and fjords. This leaves us with an inevitable question. If Mars once had this much water, it must have had conditions suitable for life. So, did that life simply vanish along with the water? Or could it have retreated, surviving invisibly just beneath the frozen surface? As we scan the Martian landscape, one feature dwarfs all others. It's unbelievably massive volcanoes. We're talking about a scale so immense that even the tallest mountains on Earth would be mere foothills in comparison. The most striking example is Olympus Mons. This single volcanic mountain is so vast that its base could cover the entire country of France. Its peak soars 22 kilometers into the sky, making it nearly 3 times the height of Mount Everest. It's quite literally a mountain that pierces the heavens. So, how could such a titan ever come to be? The answer lies deep within Mars' geological heart. Here on Earth, our crust is broken into moving plates, a process called plate tectonics. As these plates drift over stationary hotspots of magma, they form chains of volcanoes, like the Hawaiian Islands. Because the plate is always moving, no single volcano can grow in one place for millions of years. But Mars is different. It lacks active plate tectonics. This means that when a magma plume pushed toward the surface, it stayed in the exact same spot for an immense span of time. For hundreds of millions of years, lava erupted from the same vent, building up layer upon layer, growing ever larger, until it created the undisputed largest volcano in our solar system, Olympus Mons. And Olympus Mons is not alone. It stands on the edge of the Taurus Plateau, a veritable kingdom of giant volcanoes. This region is home to 3 other colossal peaks: Jezero Mons, Olympus Mons, and Jezero Mons, each far larger than any volcano on Earth. The Taurus region itself is a massive bulge on the planet's surface, covering an area the size of the United States and exerting so much weight that it has literally bent the Martian crust. Another reason for their immense size is Mars' weak gravity, which is only 38% of Earth's. This feeble pull allowed lava to flow for much greater distances, creating volcanoes that are not only tall but incredibly broad. The 600-kilometer wide base of Olympus Mons makes it a sprawling giant of truly planetary proportions. Scientists are still debating whether these volcanoes are truly extinct, While the planet's interior has largely cooled, some lava flows appear to be geologically young, perhaps only a few million years old. In the lifespan of a planet, that's the blink of an eye. If correct, it would mean Mars isn't entirely dead. A faint fire may still be smoldering deep within. These volcanoes didn't just build mountains. They shaped the entire climate of Mars. Every eruption vented huge amounts of carbon dioxide and water vapor into the air. These greenhouse gases would have trapped heat, warming the planet and making it possible for liquid water to exist on the surface. It's likely that the warm breath of these ancient volcanoes is what allowed those long-lost rivers to flow. The immense weight of the Tarsus bulge also created tremendous stress on the crust, ripping it apart from vast canyons. The most famous of these is Valles Marineris, a canyon system that stretches for 4,000 kilometers. If laid across the United States, it would span from coast to coast. Plunging to depths of 7 kilometers, it dwarfs Earth's Grand Canyon. This colossal scar is a direct result of the immense geological forces unleashed by the rise of Tarsus. But these giant structures are more than just geological wonders. For future colonists, they represent golden opportunities. The high rims of the calderas are ideal locations for solar farms, while ancient hollowed-out lava tubes could provide perfect natural shelters from deadly solar radiation. And then there is the ultimate vision, to stand on the summit of Olympus Mons, to look out at the horizon and see, with your own eyes, the gentle curve of the planet. From this vantage point, so high above the plains, you can experience something impossible on Earth, witnessing the roundness of the world from the peak of a mountain. Ultimately, Olympus Mons and the Tarsus region are powerful reminders. Mars may seem silent and still today, but it was once a world of incredible energy, dynamism, and fire. And who knows, perhaps these silent giants are not dead, but merely sleeping. The atmosphere of Mars is a mere ghost of what it could be, an almost invisible veil of air. It's so thin that the air at the top of Mount Everest would feel like a rich oxygen paradise in comparison. The surface pressure on Mars is less than 1% of Earth's, making it closer to a vacuum than a true atmosphere. So, how did a planet that once had air thick enough for rivers and lakes lose its very breath? The answer lies deep in the planet's core. Here on Earth, our greatest protector is a powerful magnetic field generated by the churning of liquid metal in our core. This invisible shield forms a bubble around our planet, deflecting a constant stream of deadly charged particles from the sun. It is a shield that protects our atmosphere and, by extension, all life on Earth. Mars once had a shield of its own. We know this from the magnetized rocks that still exist on its surface. But Mars is a smaller planet, and because of its size, its core cooled down much faster than Earth's. As it cooled, the internal churning slowed and eventually stopped. The dynamo died, and the magnetic field vanished. That was the beginning of the end. Without its magnetic shield, Mars was left naked and vulnerable before the onslaught of the solar wind. A relentless stream of particles from the sun slammed into the upper atmosphere, stripping it of its molecules and casting them out into space. It was a slow, gradual process of erosion that took place over millions of years. But in the end, Mars was stripped bare, its atmosphere lost, leaving behind the cold, dead world we see today. This process, in fact, continues even now. NASA's MAVEN orbiter is actively measuring the gases that are still bleeding away from Mars into space, a loss that accelerates during intense solar storms. The planet's slow suffocation has never truly stopped. The loss of the atmosphere was a fatal blow for water as well. With such low pressure, liquid water can't survive on the surface. It either freezes solid or instantly boils away. Without a thick atmospheric blanket to provide pressure and warmth, the rivers and lakes were doomed. While the Martian atmosphere is mostly carbon dioxide, a potent greenhouse gas, it's simply too thin to trap any significant heat. As a result, the planet experiences extreme temperature swings, plunging to below -100 degrees Celsius at night. This wild instability creates a brutal and unforgiving environment. Some scientists have proposed ambitious plans to re-thicken the atmosphere, perhaps by vaporizing the frozen carbon dioxide at the poles, but the calculations are grim. There simply isn't enough accessible CO2 left on Mars to make a meaningful difference. The ingredients to rebuild its atmosphere are gone. Adding to the problem are the planet-encircling dust storms. These colossal tempests can shroud the entire world in dust for weeks, and as the dust warms the upper atmosphere, it makes it easier for what little air remains to escape into space. To understand just how catastrophic this loss was, imagine if Earth lost this magnetic field. Our oceans would boil away, our air would be stripped into space, and our blue planet would become as silent and barren as Mars. The red planet stands as a stark reminder of what happens when a world loses its shield. This vanished atmosphere has profound implications for our future on Mars. The lack of air and a magnetic field means the surface is constantly bombarded with deadly radiation. The open sky is a lethal hazard, forcing any human colony to be built underground or within heavily shielded habitats. In the end, the story of Mars' lost atmosphere is a cautionary tale. It teaches us how fragile an atmosphere can be. As we confront the challenges of climate change on our own world, Mars serves as a clear and chilling example. Without its breath, the planet has no chance at life. We have spoken of the massive ice deposits buried beneath the Martian soil. These are more than just reservoirs of frozen water. They are archives, frozen in time, holding the secrets of Mars' long-lost climate. Just as Earth's ice cores allow us to read our planet's past, the glaciers of Mars act as a frozen diary. To understand the climate of Mars, we must first look at its wobble. Mars has an axial tilt of about 25 degrees, very similar to Earth's. But there's a critical difference. Earth is stabilized by the gravitational pull of our large moon, which keeps our tilt relatively steady. Mars, with only its two tiny moons, Phobos and Deimos, has no such stabilizer. As a result, its axial tilt swings wildly over millions of years, from as low as 15 degrees to as high as 45. This wobble is the engine that drives Mars' dramatic climate cycles. When the tilt is high, the poles receive more direct sunlight, causing the polar ice caps to vaporize. This water vapor then travels through the atmosphere and falls as snow in the mild latitudes, creating vast glaciers. When the tilt is low, the poles get colder again, and the ice retreats from the mid-latitudes back to the polar caps. The entire surface of Mars essentially breathes, with water migrating back and forth in a slow, planetary rhythm. Today, radar observations have confirmed that massive glaciers still exist, buried beneath a protective layer of dust and rock in the mid-latitudes. They are relics of a time hundreds of thousands of years ago when the planet's tilt was different. This dusty blanket is what allows them to survive. preventing the ice from turning to vapor in the thin air. The polar regions are even more dramatic. Here we find vast layered ice caps made of both water ice and frozen carbon dioxide, or dry ice. Each winter, a significant portion of the atmosphere freezes out, coating the pole in a seasonal cap of dry ice. When spring returns, that ice turns back into gas, causing huge swings in the atmospheric pressure. This cycle is the very heartbeat of the modern Martian climate. These ice caps are built up of thousands of distinct layers. Much like tree rings on Earth, each layer in the ice tells a story of a different era in Mars' climate's history, corresponding to a period of a different axial tilt. By studying these layers, scientists can read the planet's past like a book. But this ice is not just a scientific treasure. It's the key to our future on Mars. For future explorers, ice is as precious as gold. From it, we can get water to drink, oxygen to breathe, and hydrogen for rocket fuel. The buried ice of Mars is both a lifeline and a potential ticket home. This brings us to one of the most tantalizing mysteries on Mars today. On some slopes, dark streaks appear during the summer and fade in the winter. For years, scientists thought these recurring slope lines were the signature of flowing, briny water, proof that liquid water still exists on Mars today. More recent studies, however, suggest that they might just be flows of dry sand and dust. The debate is fierce and ongoing. Is it a geological illusion? Or are we seeing a planet that is still, in some small way, alive with flowing water? These climate cycles are also critical when considering the possibility of life. During periods of high tilt, conditions for liquid water near the surface would have been much more favorable. If life ever did arise on Mars, these warmer, wetter periods could have been its oasis in time. This means any potential Martian life would have been locked in a constant battle for survival, advancing and retreating with the planet's ever-changing climate. These ancient glaciers also left their mark, carving the landscape just as they did on Earth. We can see moraines, glacial valleys, and other features that prove ice was once an active, powerful force on Mars. Ultimately, the ice on Mars tells a story of both the past and the future. It holds the record of a world that was once more vibrant, and it offers the most vital resource for a future human presence. The white ice, hidden just beneath the red dust, may be the single most important key to unlocking a permanent future for humanity on Mars. A planet's destiny is written not just on its surface, but in its very core. Here on Earth, our active molten core is the engine of our world. It generates the magnetic field that protects us and drives the plate tectonics that constantly reshape our planet. But when we look deep inside Mars, we find a very different story. The story of a heart that has grown quiet, faded, and slowly frozen in time. Like Earth, Mars has three basic layers: a crust, a mantle, and a core. But the difference in size changes everything. With only half the diameter of 1/10 of the mass on Earth, Mars was destined to cool down much faster. While Earth's heart still bears hot, the core of Mars has largely solidified. This single fact sealed the planet's fate. The Martian crust is thick and rigid, in some places twice as thick as Earth's. This heavy crust made it difficult for internal heat to escape, which helps explain why volcanoes like Olympus Mons could grow so large, but also why volcanic activity eventually ceased. Once the planet's internal heat engine began to fail, volcanoes fell silent. Beneath the crust, the Martian mantle is also much more stagnant than Earth's. It lacks the dynamic convection currents that drive plate tectonics on our world. Without moving plates, the crust remained a single, solid shell. This is why volcanoes could grow to such immense sizes in one spot, and why the geology of Mars followed such a different evolutionary path. But the most critical difference lies at the very center. We believe the Martian core is made of iron, nickel, and sulfur. But because of the planet's smaller size and lower internal pressure, it couldn't retain its heat. It cooled, it solidified, and the dynamo that generated the planet's magnetic field died. With that, Mars lost its most important defense. NASA's InSight lander, by listening for Marsquakes, gave us our first real glimpse into the planet's interior. Its data confirmed that the core is large but less dense than Earth's, suggesting it's mixed with lighter elements. It painted a picture of a heart that is now mostly frozen and silent. The death of the core had a cascade of devastating effects. It didn't just kill the magnetic field, it choked off the planet-wide volcanism that had once supplied the atmosphere with heat and gases. Slowly but surely, Mars was dying from the inside out. While the small Marsquakes are still detected, they are not the signs of a dynamic planet, but the faint tremors of a world slowly contracting as it cools. However, Mars may not be entirely dead. Some models suggest that the parts of the core could still be molten, and InSight's data hinted at the possibility of faint thermal plumes in the mantle. If true, it means that deep inside a tiny spark of the planet's ancient fire could still remain. This internal cooling had profound consequences for life. A geologically active planet with a magnetic field provides a stable, protected environment. By losing its internal heat, Mars lost its ability to protect its atmosphere, regulate its climate, and shield its surface from radiation. While any surface life would have been doomed, it's possible that deep underground, shielded from the harsh conditions, microbial life could still be clinging to existence. For future human explorers, this geological silence is a double-edged sword. On one hand, the planet is stable, no major earthquakes or volcanic eruptions to worry about. But the downside is lethal. Without a magnetic field, the surface is constantly bathed in deadly radiation, turning the beautiful, open sky into a fatal hazard. Ultimately, the story of Mars' interior teaches us a fundamental cosmic lesson. Size is destiny. A small planet loses its heat quickly. Its core freezes, its magnetic field dies, and its surface becomes a barren wasteland. A larger planet can keep its heart burning for billions of years, maintaining its shield and nurturing the possibility of life. Mars is the solar system's most tragic and striking example of this truth. From the moment we first looked to the heavens, we have asked the same question: are we alone in the universe? In the search for an answer, no world has captivated us more than Mars. It is, after all, the most Earth-like planet in our solar system, not a scorched inferno like Mercury, nor a frozen giant like Neptune. Its day is similar length to ours. It has seasons, and it occupies that tantalizing space where conditions could have been just right. This is why, for many scientists, Mars remains the single best candidate for finding life beyond Earth. When we talk about life on Mars, we are talking about two different timelines. the ancient past, and the present day. For the past, the evidence is compelling. As we have seen, Mars was once a warmer, wetter world with lakes, rivers, and a thicker atmosphere. The three key ingredients for life as we know it: liquid water, an energy source, and a diversity of chemical elements, were all present. But what about today? This is where the mystery deepens. The surface is hostile, with its thin air and intense radiation making it impossible for liquid water to last. Underground, however, could be a different story. In aquifers deep below the surface or in protected lava tubes, pockets of liquid water might still exist. If they do, these would be ideal sanctuaries for microbial life to endure. Over the years, a few tantalizing clues have emerged. The most famous came from a meteorite that was blasted off of Mars and later landed on Earth. It was found to contain microscopic structures that looked tantalizingly like fossilized bacteria. The discovery made headlines around the world, but further studies showed that these structures could also have been formed by non-biological processes. It wasn't the smoking gun, but it forever ignited the passion for the search. Today, that search is being led by rovers like NASA's Perseverance, currently exploring Jezero Crater, the site of an ancient lake and river delta. Perseverance is drilling into rocks that formed in this watery environment, collecting samples that might contain the chemical fingerprints of past life. These samples are being stored for a future mission to bring them back to Earth, where our most advanced labs can analyze them. If they are found to contain biosignatures, it would be the single greatest discovery in human history. Another lingering mystery is the presence of methane. On Earth, the vast majority of methane is produced by living organisms, and periodically, faint plumes of methane are detected in the Martian atmosphere. They appear, then they vanish, and their source remains a complete enigma. It could be a geological process, or it could be biological. Each new detection sends a wave of excitement through the scientific community. Ultimately, the search for life on Mars is more than a scientific question. It's a philosophical one. If we find that life arose independently on our nearest neighbor, it would suggest that life is not a miracle, but a common cosmic occurrence. But if we find that Mars has always been lifeless, it would underscore just how precious and rare our own living world is. Even if we were to find life, the questions wouldn't stop. We would then have to ask, did it evolve on Mars independently, or was it seeded from Earth? Or vice versa, carried across space on meteorites? Finding life on Mars wouldn't just be an answer. It would be the beginning of a whole new set of questions. In this way, Mars holds up a mirror to us. Whether it once harbored life or was always barren, the answer will forever change our understanding of our place in the universe. For centuries, Mars has been a symbol of both fear and hope. To the ancients, it was the god of war. Today, it stands as a symbol not of conflict, but of a new beginning, humanity's potential second home. But can we truly live on Mars? Let's break down the challenge. First, we have to be realistic. Mars is an incredibly hostile environment. The thin atmosphere, the freezing temperatures, and the constant bombardment of solar and cosmic radiation make the surface a lethal place. Without heavy protection, an unprotected human would receive a fatal dose of radiation in a matter of months. Survival on Mars starts with one thing: a very good shield. This is why many designs for a Mars colony focus on living underground. The ancient lava tubes that riddle the planet's subsurface are perfect natural shelters. They provide excellent protection from radiation and buffer against the extreme temperature swings on the surface. NASA and SpaceX both see these caves as key to establishing a permanent human presence. Other ideas involve giant, inflatable domes on the surface, creating pressurized, Earth-like habitats. But the risk is immense. A single tear or leak would be catastrophic. For this reason, many believe that going underground is the safer and more suitable option. Of course, colonists will need water and food. The water is there, locked up as ice at the poles and underground. Robotic missions could mine this ice, providing water for drinking, oxygen for breathing, and hydrogen for rocket fuel. Food is trickier. The Martian soil is toxic, laced with chemicals called perchlorides. This means colonists would have to rely on advanced, self-contained agricultural systems like hydroponics and aeroponics, growing food without soil at all. Energy will be another critical challenge. Solar panels are a good option, but Mars is prone to planet-encircling dust storms that can block out the sun for weeks at a time. This is why the most reliable source of power for a nascent colony would likely be small, compact nuclear reactors. But just getting there is a monumental challenge. The journey to Mars takes 6 to 9 months, a long time to be confined in a small spacecraft exposed to the radiation of deep space. Because of the difficulty, the first Martian colonies would have to be almost completely self-sufficient. This won't be about visiting, it will be about staying. Visionaries like Elon Musk believe that a self-sustaining city on Mars is possible within our lifetime, with his Starship designed to one day carry hundreds of people at a time. While the vision is inspiring, the technical and logistical hurdles are enormous. We have yet to build a permanent city in Antarctica. Mars is orders of magnitude more difficult. And yet, the dream of a Mars colony is about more than just technology. It's about the future of our species. Think of the first child born on Mars. They would be the first true Martians, living their entire lives under a different sky. Their existence would mark the moment humanity became a multiplanetary species. Despite all the challenges, the dream of Mars endures. Because going to Mars is more than an adventure, it is an insurance policy. In the event of a global catastrophe on Earth, an asteroid impact, a supervolcano, or a climate collapse, a self-sufficient colony on Mars could ensure the survival of humanity. Colonizing Mars won't happen tomorrow, but the first steps are already being taken. The robots are our scouts, the rock samples are our first clues, and the technologies we're developing today are the foundations for that future. Perhaps not in our lifetime, but in our children's, the red dot in the night sky may transform from a distant world into a new home. When we look to the future, we can imagine 3 possible destinies for humanity and Mars. In the first scenario, Mars remains as a scientific outpost, a place where scientists and explorers visit, conduct research, and then return, much like Antarctica today. It would be a laboratory, not a home. In the second scenario, we establish permanent colonies that grow into self-sustaining cities. Over centuries, a new branch of human civilization would take root under the red sky. They would start by relying on Earth, but eventually they would become truly independent, generating their own air, water, and food. Mars would become humanity's second home. The third scenario is the most ambitious of all. Terraforming. The dream of completely re-engineering Mars to make it Earth-like, thickening its atmosphere, warming its surface, and releasing its water. While scientists have proposed ideas from orbital mirrors to deploying greenhouse gas factories, the sheer scale of such a project is beyond our current capabilities. For now, a blue Mars remains in the realm of science fiction. So why is Mars so important? Because it's more than a destination. It's a driver of innovation. To get there, we must invent new forms of propulsion, life support, and energy generation. The solutions we devise for Mars in water recycling, renewable energy, and sustainable agriculture could have transformative benefits back here on Earth. But the philosophical dimension is even greater. The act of going to Mars will force us to redefine who we are. Are we a species confined to one planet, or are we designed to become a multi-planetary civilization? To succeed would be a revolution not just in technology, but in what it means to be human. It's also critical to remember that going to Mars does not mean giving up on Earth. This is our home, a paradise of oceans, forests, and life that is unequaled anywhere else we know. No matter how advanced our technology, a city on Mars will always be a fragile bubble in a hostile world. The dream of Mars should inspire us not to abandon Earth, but to appreciate and protect it even more. Imagine the history books of the future. Perhaps they will contain a simple sentence. In the 21st century, humanity first set foot on another world, and in the centuries that followed, they put down roots. If we achieve this, our place in the cosmos will be forever changed. We will no longer be the people of one world, but of two. The future of Mars is inextricably linked to our own. Perhaps some of our children will be born on its soil. Perhaps our grandchildren will play under its pale red sky. And perhaps one day humanity will use Mars as a stepping stone to worlds even further away. Because Mars is not the end of the journey. It is the starting line. And so we are left with the final, defining question. Is Mars destined to be humanity's graveyard or its second cradle? We don't yet know the answer, but one thing is certain. We have begun the journey to find out, and there is no turning back.